Now I want to use this idea of detail balance, which is light coming into a system is equal to the light leaving the system under dynamic equilibrium, and apply to the concept of light trapping. And this is nice because we saw this already before, and you're going to see this in a little more detail later on. But let's try to understand what is light trapping first very, very quickly. If you have a parallel slab of light, material here, like silicon, which is perfectly polished on both sides, light comes in, it simply refracts and leaves at the same angle. So this angle, theta, is equal to this angle, theta. I think this was part of one of the homework early on, so you're very familiar with this. Now I can put a mirror here and simply fold the beam back into the material. So then I get two passes. Now I'm trying to increase this path length inside the material because that increases the probability that it will be absorbed. That's what I'm trying to do. I'm trying to absorb that light. Right? That's what a solar cell should do. So here I'm getting an extra pass here. Right? I get more light, more travel length. And I can put a pyramidal shape here and even increase this even further. And I can make it random. I can increase it even further. I can make two surfaces random. I can increase it even more. So you can start thinking about this. Yeah. 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 So there are two reasons. So first of all, one problem with this, which you didn't talk about too much, is something called surface recombination. So when you texturize the surface, you're damaging the crystal structure of silicon. So that means you have defects in the crystal structure, and this is bad. These defects in the crystal structure essentially give rise to intermediate energy levels in the band gap, and the electron holes that are generated in the silicon will get trapped there. They will not reach the contacts and contribute to current. And this is the recombination law. So if you remember, we talked about the external quantum efficiency plot. And it looked like this. In the middle, I had nice high quantum efficiency, but over here it starts dropping. And that's because of this recombination loss. The carriers are not reaching the contacts. They get trapped in these defects. So that's a problem. There are ways to avoid this. So I would say most of the most advanced solar cells, they do this with something called passivation, which is a way to get rid of these defects. Now, slightly older solar cells, they would actually use this because this was another way to get some amount of trapping, but still maintain a relatively good crystal structure, because this dimension here is much larger than the crystal lattice dimension. So it's always a trade-off. It's kind of an engineering trade-off. Okay, so yeah, well, there are. This is changing dramatically. A lot of people are working on all kinds of things. Yeah, so it's a very, very exciting area as well. By the way, here I treated this as a mirror, but this can also be a conductor. So this can be a mirror and a contact, right? Can be both, and it's usually both, something like molybdenum or aluminum and so on. Lots of really, really cool stuff is happening there as well. So these are examples of what they look like in the micro scale. So these are microstructures of more or less random structures, silicon, essentially. Sometimes it's glass, because you can use glass to essentially protect the silicon. So the silicon is underneath, so you can't see it. But I'm quite certain these are both silicon. You can get many different textures. Now, why do we want light trapping? We want to trap the light to reduce the thickness of the cell. So let me go back here. Oops, sorry, accidentally. So here, if I can get a very long path length by using a very thick material, right? If I use a very thick material like that, I can get a very long path length, but that's expensive and it's harder to handle. So in order to use a very thin material and still get lots of bounces around here is where I use this texture. That's the reason why you want to do the light trap. Reduce the cost. And also it has some advantages from the semiconductor perspective, because thinner materials, you can make them purer, easier to make them purer, fewer defects, and less, the carriers don't have to travel far, right? The contacts are right there, really close. So you have fewer chances of recombination losses. Now let's, oops, wait. Okay, now let's apply our analysis from before to this textured solar cell with absorption taken into account. So we ignored absorption before, now we're going to add it. And the only assumption we're going to make is that the absorption is weak. So it's mostly transparent, which is true in the case of silicon near its band gap. So again, we're going to do the same analysis. Before, the input light is simply, now we are talking about power. Okay, this is power. So it's the area multiplied by intensity, watts per meter squared, multiplied by some probability that it transmits the interface. This is the power coming into the solar cell, textured solar cell. Okay. Now we have the escape, which is the escape cone, as same as before. Again, we have an area, intensity, and some escape probability, and then we have our familiar term 2n squared from before. Exact same equation. Now, the only new thing here is that we're introducing an absorption. Light is absorbed at the interface during the reflection, and we have to somehow model it. And the very simple model is to use, okay, I have an area, I have some sort of efficiency, which is the fractional absorption, and then I have the same as intensity and the similar integrals as before. And this we know how to do, and we end up with a very simple expression here, which shows that the absorption is simply proportional to some eta. Okay. Fractional absorption efficiency. Now, this is not the only thing that happens. This is the inter-absorption that happens at the interface. Of course, most of the light's absorbed in the bulk, or that's what you want, right? You want the light to be absorbed inside the silicon, so it will create electron hole pairs and create a current. So this is the light absorbed in the bulk, which is really what we want. And that's a bit more complex to model, so we won't go through in great detail, but it is really dependent on something called the absorption coefficient alpha here, which is the probability that if a photon comes in, it will actually be absorbed. And that depends on the external quantum efficiencies. So keep that in mind. So it actually connects back to it, depends on the energy of the photon and so on. And the rest of the stuff is simple because this is the internal intensity. This is just the volume that you're considering, a small volume element. And d omega over 2 pi is simply the integral over the solid angle, because you're integrating over a sphere inside this material. I want to clear all that. So the expression, once you go through the integral, it becomes quite simple. You have a term 2 alpha L, where L is essentially an effective thickness of the materials. Remember, these are not flat, so there's no exact thickness. You have to define some sort of effective thickness because of the texturing on the top and bottom. Okay, so those are the three terms. Now we just need to do detail balance. It is not related to absorption, but it will affect their absorption. And by the way, the anti-reflection coating in lenses is very different than in solar cells. In lenses, we use the dielectric grating, which uses the quarter wave lambda over 4 stack, which we talked about also in class. And there's a very specific reason for that. The reason is because in lenses, you want to preserve the angles. You don't want to lose the angle. Because if you randomize the angle, you've lost the information of the object, right? Another way to say it is that for a lens, you want to be able to see through it, transparent. You want it to be completely transparent. In the case of light trapping for a solar cell, you don't care. You can work with a frosted glass. That's just another way to think about it. And what else this is absorbing? Not transparent, at least a visible wavelength. So in that, mostly, not 100%, but mostly, because we do use it for optics. But it behaves just like any plastic. So it is a polymer. Oops. So we now, coming back to this, now we can apply detailed balance. You have light in equals light out. Okay, what is light in? That's simple. That's my first term here, right? Incident light, area, apply the probability. What's light out? I have a term that shows the escape cone. I have some absorption that happens at the interface. That is light out because I'm losing the light. And then I have some absorption that happens in the bulb. Right? Those are the three things that will happen. Light coming in, some light escape, some light got absorbed at the interface, some light got absorbed in the bulb. Okay, that's conservation of energy. I put it all together. I get a very simple expression for the internal intensity related to all these terms here. So one thing you'll notice is that previously when we did not have absorption, this disappeared and this disappeared. And we essentially got this 2n squared term, right? 2n squared times whatever is outside. Now the enhancement is reduced because of the absorption that's happening, which is expected, right? Because you've lost light by absorption, which is a good thing typically because you want to absorb that light. Your total enhancement has gone down. So which means that you have to be careful how you do these designs. The more you have absorption, the less enhancement you'll get. And less enhancement you have, the less absorption will happen in the bulb. So these kind of could be mutually exclusive. So something to be aware of as well. Now, for us today, I mean, in this class, we're interested in increasing the absorption in the solar cell. So now we can find an expression for the absorption that is desirable. And that is here. This is the absorption in the bulk. And that this equation can easily give that. And you get a relatively simple expression here. And we can simplify this further by looking at just the efficiency, which is what is the fraction of incoming light that is actually absorbed in the solar cell, in the bulk of the solar cell. And oops, and that's what's shown here. And what does it depend on? It depends on this alpha L term, which is intuitive. Higher my alpha, the higher the chances of absorption. Higher the L, which is this effective thickness, which is the path length to some extent, higher the chances of absorption. So those are expected. The other things at the bottom are also important. So let's try to simplify them to understand how those affect it. Actually, let me go back because I forgot to write. So here, I can make a few assumptions here. Now I'll come back to this soon. These area of escape and area of incident, I'm going to say they're the same. More roughly the same. Because keep in mind, okay, I have a textured cell here, I have a textured surface here, and I have some sort of mirror at the bottom, right? So the area that light can come in and the light escapes is roughly the same, I can say. I can also say area that of reflection is roughly equal to the area of incidence, so I can ignore those. And then I'm also going to say this is approximately 1, and this is approximately 1. So if I do all those simplifications, what do we get? 2 alpha L divided by 1 over 2n squared plus eta over 2 plus 2 alpha L. Now, oops, can't see. Now, again, if I had very small, if for instance, what is my eta? Eta is my fraction that's absorbed at the interface. And I'm gonna, if I ignore that, I end up with an expression shown here. What does it mean? That means the lower the absorption. So how do I maximize this? To maximize this, the only things I can do are increase alpha, increase L, or increase N. It is satisfying because that it makes intuitive sense as well. Increasing N makes intuitive sense because that increases my upper limit of the intensity of light I can achieve inside the material. Okay, let's look at this more closely. So we're going to consider the case of weak absorption. Silicon is an indirect band gap semiconductor. What does that mean? That means, oh, my thing doesn't, sorry, it looks weird on my, I guess, okay. The transition of absorption of a photon and creation of the electron hole pair is more difficult to do in the case of an indirect band gap semiconductor like silicon. And what that means for this analysis, that alpha is small. We can also assume eta is small, which is the absorption loss at the interface, as I've just said. This is the ideal case, and the other things are the same thing as I said. So if alpha L is small, so I'm going to write the same expression that I wrote down before. This is what we had. Okay. If I'm going to say this is a small number, I can take that down. Right. And this turns out to be something like, so what's the maximum I can hope to get? Right. Actually, this is not good. Right? So if I make these assumptions and I say the alpha is small, the maximum I can hope to get is 2 times 2n squared, which is 4n squared. I made a mistake in my write-up before. There, the alpha L is dropped from the previous expression. Actually, let me just point that out. That was my mistake. This cancels. Let's just make sure. They say that's 1, that's 1. Oh yeah, I forgot the 2 here. That's why you get the 4n squared. Okay. This is approximately equal to 4n squared alpha L. Yeah. Now alpha L, I can, okay, normalize that to be about 1. So that's where the 4n squared comes relative to alpha L. Alpha L is just the absorption path length. Okay. Anyway, the algebra is not terribly important, but the key thing here is that that factor of 4n squared is quite critical. Now, how does this actually come into play in actual practice? So in the paper, there's a very nice experiment, which is really simple, elegant to understand. Okay, the experiment is what's shown in this picture. There's a white surface, which is our mirror, basically. And there's a silicon wafer in front of it, okay, which is right here. Now, there's an integrating sphere. That just means that it will collect all the photons that is incident on the surface and count them. That's basically all it does. So light's coming in from that side. Now, polished side is facing the light. So you would expect all the light to simply reflect that and be collected in the integrating sphere. By the way, the way you get the light here is that there's a little hole in the integrating sphere. It's not drawn, that's all. And the rear surface of the silicon wafer is either flat and polished like a mirror, or it is textured. So he is trying to do an experiment with a fully polished 2 parallel side silicon wafer, or where one side is textured, and see what the difference is. What do you expect to see? In the case of the fully polished side, we would expect most of the light to simply reflect that. So I would get a very high signal. In the case of texturing, I would expect some of the light to be trapped inside the silicon. So, and I would get less light reflected back, and I would measure lower signal. Right? By a big factor, 2n squared, right? That's what we calculated. And is that really true? And the answer is yes. It's exactly what you measured. And that's what's shown here. There are 2 things that happen. So you can see this is the polished case, and this is the textured case. And you can see the signal has dropped. So absorption has increased, the signal dropped. The other thing that has happened is that the absorption band has redshifted, which is actually a good thing in the case of silicon, because you're pushing the band of absorption into the regime that is more efficiently absorbed by the silicon solar cell. Now, by the way, this is a spectrum, it's not a number. So this integrating sphere also resolves the spectrum. That's where the band edge is important. The band edge of silicon is important, which is about 1.1 and about here. So pushing it this way is good thing because you're absorbing all those photons, which you would have otherwise lost. Here, keep in mind the wavelength is decreasing that way, but the energy is increasing that way, right? Remember, they're inversely proportional. Now let's look at one more example, which is a very interesting example, actually. It is not just simply texturing, but imagine if we could make little silicon microspheres and have them act as solar cells. It's not exactly true, but let's imagine this thought experiment. And now they are embedded in some polymer, transparent polymer, in this case PMMA or plexiglass, and there's a white backing to serve as a mirror. Now, what does this mean? This means now we have a very, very, very thin, flexible piece of polymer sheet, like plexiglass, which is embedded with silicon solar cells, very small silicon spheres like that. So they're cheap, covers small area, but most of it is transparent, right? Light can pass through normally, if you think about it. However, because of the random nature of the textures, what happens is that you actually end up with lots of the light trapped within this polymer sheet, and it will end up being absorbed by the silicon solar cell. So what you observe in such a situation is that you get a lot more current than if you did not have that textured plastic and you just have those silicon spheres. So it's a way to make a very, very cheap absorbing film. And of course, in this case, it was just an experiment. So here again, silicon microspheres are embedded in the PMMA. Light is trapped in the silicon due to the higher index and texturing. And it enhances the absorption. Now, we can do the detail balance calculation. Again, yet another example of detail balance, which is energy conservation. It's good to kind of understand this because we have done it. This is the third time we'll do it. So what are we doing? What are the things that will happen? Light can come in from air into the plastic or PMMA. Light can go from silicon to the PMMA, which is the escape, right? And then on the other side, light can go from PMMA to the air, plus light can go from PMMA to the silicon. So those have to balance. So air to PMMA, silicon to PMMA, that's what's coming into the plastic or escaping. Here we are using PMMA as the control. And here light is going from PMMA to air and then PMMA to silicon. You can do it with respect to silicon, you can do it with respect to PMMA. You'll get the exact same result. And the equations are exactly the same as before. We have light coming in from air to PMMA. The indices are defined such that N2 is silicon, N3 is PMMA, N1 is air. So you get the exact same expression, except that now you have these terms 1, 3, 2, 3, and so on, which just shows which direction the light is going. So this is in from air to PMMA, and this is silicon to PMMA. And the same thing on the other side, you have PMMA to air and then PMMA to silicon. The I3, for instance, is the intensity of light inside the plastic of the PMMA. Okay, you can do the details balance calculation in silicon, where you have light going from air to silicon, PMMA to silicon is equal to silicon to air, silicon to PMMA, but there is also absorption in silicon, an extra term here. And that is this term here. You get the expression as before. You have two equations, you can solve them. And what are we trying to do? We're trying to find the absorption in the silicon. And that's just a simple algebra. So we can plug in numbers, and this is silicon. This is the PMMA, refractive index. This is the transmission from air into the silicon with an anti-reflection coating. We're assuming it's quite high. And then we get an intensity enhancement shown here. And we are going to assume that we are close to the band gap of silicon, so alpha is small, then we get an intensity enhancement of 2N2 times I1. So again, N2 is 3.53, so this is a pretty big number, right? Greater than 18. Okay, now of course we are interested in the absorption, so let's look at the absorption. And the this is actually the experiment. The experiment is again very similar to what was shown before, but in this case, instead of having a wafer, it was a plastic film embedded with the silicon granules. So if you don't have the silicon granules, everything is reflected back, so you get very high signal. Once you add the silicon granules, it drops dramatically because of this light trapping effect, and the signal drops. There's also the shift, but that's not so important. So here you can see this is flat because it's mostly PMMA, right? It's just a piece of transparent plastic, but there's a mirror, so light just bounces back. There's a mirror behind the PMMA. Oops. Oh, okay, that's my last slide. Okay, good. So just a very brief summary, what we have talked about, maybe two things that are important. One is the idea that by texturing the surfaces, you can increase the intensity of light inside the material. And you can take advantage of this with a backing reflector to increase the absorption of light in a solar cell. This is something you will learn in a bit more detail next week, but you have a picture of that. And the second thing I want you to get from this is how do you do this analysis? And that analysis is the whole basis of statistical ray optics, which has to do with, okay, I have detail balance, I have light coming into a system, light leaving the system, and light absorbed by the system. I need to make sure those are all equal. By simply making them all equal and applying very simple geometrical optics principle, we can come up with really straightforward and intuitive design equations. So you will appreciate this more also next week when we talk about light trapping. It's actually important both for solar cells as well as for light emitting diodes, LEDs. Okay, with that, I want to talk about the last assignment a little bit. So let me actually go to this. Oh, actually, before I do that, I'm going to switch this one out. I think this is time. Second. So the assignment, let me make sure this is connected. Sorry. Okay.